Everyone, today we're going to talk about gravitation. So, it's the force of gravity everywhere in the universe, right? Which means that any body with mass has gravity, which means that mass attracts mass, which means then that everything that is made of protons, neutrons, and electrons, everything that is made of matter, from the definition that we have of matter, has mass, which means there's a force of gravity pulling everything together. Gravity is the weakest of all the forces of nature. We have the four forces are gravity, electromagnetism, which is involved with charges and attraction and repulsion between particles, and you also have the weak force, which causes radioactivity and aging and decay, and the strong force, which keeps the atoms together, right? So gravity is the weakest of all the forces because you can only experience gravity if you have a large quantity of matter, right? We can say that the universe is made of matter and energy. According to Einstein's famous equation, E equals mc squared, which means energy can be converted to mass, and you multiply the mass in kilograms times the speed of light squared, and you get the energy. So everything that we see around us is energy, or matter, but matter is also energy, and all matter attracts matter, right? And we have all the galaxies and the solar systems and the planets and the asteroids all interacting gravitationally. We also have gravitational waves, ripples in space-time, and the propagation of these forces throughout the universe. Now, gravity. So we have gravity between the sun and the planets, between us and the planets, between a moon and a planet. The equation for gravity is G, big M, little m, over r squared, where in this particular example, one of the big M represents the mass of the sun, little m the mass of the planet, G is the gravitational constant, which is a constant of proportionality. It's a constant that when you plug it in the numbers, the variables, with a specific value, that big G, the gravitational constant, allows for the measurement of a force. R is the distance between the center of the two objects. So notice, however, that gravity comes from the center of the object. So whenever you want to find the gravity between two objects, you're finding the gravity between their center of mass. So if we set Gmm over r squared equals to mv squared over r, we're setting the gravitational force to be equal to the centripetal force, because because gravity may lead to objects moving in a circle around a heavier object. In fact, the sun, if you take the sun and the planet, they're both orbiting their common center of mass. But because a sun is much bigger and heavier than a planet, the center of mass between the two objects, most likely it's closer to the sun, which means that the sun would wobble around that center of mass between the two objects. Well, the planet is also wobbling, but because the planet is further away from the center of mass of the two body system, it seems to orbit it in an elliptical pathway. In this equation, v is the speed that a planet orbits the sun. R omega, v, is equal to the speed, so where omega is the angular frequency of the orbit. And it's angular frequency means that it's how many degrees per period, or how many, because we know that a circle has 2 pi degree radians. So if you do 2 pi over the period, you get the angular velocity, I should say, the angular frequency. And if you multiply that times r, you get the actual speed in meters per second. So when we talk about gravitation and we're talking about planet, we're also talking about Kepler's 3 laws. On the shoulder of giants is where scientists sit by learning from what scientists in the past discovered, which is recorded in books, and then refining this knowledge with better explanations by adding more discoveries to them with regular updates. Kepler's three laws, for example, are in perfect agreement with Newton's conception of gravity. Kepler's three laws are the following. Number 1, the orbit of planets are elliptical. Number 2, the planets sweep equal areas in their orbit in equal amount of time. Number 3, the square of a planet's orbital period is proportional to the cube of the planet's average distance to the Sun. This means that the planet orbits an elliptical pathway around a star, that there's a point in the orbit where the planet is closer to the Sun, and there's a point in the orbit where the planet is further away. And then when the planet is closer to the Sun, it moves faster. When the planet is farther away from the Sun, it moves slower, which gives rise to our second law. In the next page, there's a proof for Kepler's third law. Those discoveries were made from observations recorded by Tycho Brahe on the motion of planets, the Moon, and the Sun performed before the invention of the telescope. A pattern of these motions was noticed, but only later would equations be used into describing the motion with more accuracy and precision. Proof. The force of gravity between the Sun and the planet is Gmm over r squared. One of the m's is one of the object, the other m is the other object. Where g is the gravitational constant, big M is the mass of the Sun, little m is the mass of a planet, and r the distance between the center of the Sun and the center of the planet. By setting the force of gravity equal to the centripetal force that keeps the planet moving in an orbit around the Sun, we get the following. Now, if we simplify this, the little m, which describes the mass of which represents the mass of the planet, they cancel out, and also one of the r's cancel out. So you can actually find the speed of the orbit by taking the square roots of both sides of this equation. Square roots of big G times m over r gives you the speed that a planet is orbiting the star, or the speed that a satellite is orbiting the Earth. Assuming just for convenience that the orbit of planets is a circle, whose circumference is 2 pi r. So the perimeter of a circle is its circumference. So I know the orbit of planets are elliptical, but let's assume it's circular, with r being the average distance between the planet and the Sun. V, which is the speed that the planet orbits the Sun, is equal to this, 2 pi over t, where t is the period, how long it takes for one complete orbit around the Sun or a moon around the planet. By plugging this result into previous equations, we get this. You're plugging in 2 pi r over t inside the v, which is square. This simplifies to g over 4 pi square r cubed. Where did the r cubed come from? In this equation, this r becomes square. When you multiply this r with this r, you get r cubed. And then you can bring the t squared to the left. So we know that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun, which is Kepler's third law. So this is gravitation. This is a brief introduction to gravitation, Newton's famous equation Gmm over r squared, and Kepler's three laws and the proof for it, and so forth. So this is the first video on gravitation. There's going to be another one. See you there. Hello everyone. Today we're going to talk about the part 2 on gravitation. So we know that the equation for gravity between two objects is big G m over r squared, where big G is the gravitational constant, a constant of proportionality that allows us to find the force between the objects. The two m's are the masses of the two objects, and r is the distance between their center of mass. Now we know that the force of gravity is Gmm over r squared. So if you're standing on the surface of the Earth, the gravity between you and the Earth is your weight, which is mg, mass times gravity, the acceleration due to gravity. And this is also equal to the Gmm over r squared. If you know the mass of the Earth, and if you know the gravitational constant's value, which is 6.67 times 10 to the negative 11 plus some units, and r in this case would be the radius of the Earth, because that's the distance between you and the Earth's center. So you can actually find that your weight will equal the force of gravity. in that equation. Now, a planet's gravity on its surface can also be found with this equation because the little m, which is the smaller object on the surface of the Earth, the little m's, they cancel to generate this equation here. So you can actually find the gravity, the acceleration due to gravity in any planet's surface if you know the mass of the planet and the radius of the planet, assuming the planet is a sphere. This is a picture of Perseus double cluster that I took with my telescope that I decided to put here next to my drawing of the Earth. So, when objects move in a circle, they undergo acceleration because there's a change in direction, which according to Newton's first law end up being pulled outward. So like for example, when you rotate a string and there's a mass at the end of the string, when you rotate it, you generate a centripetal force that is equal to the tension in the string. But because of inertia, the Newton's first law, this object is sort of thrown outward, like probably the centrifugal effect from the centripetal force. You can actually generate artificial gravity with that. So where v is the speed that you rotate in it, and r is the radius of the turn. So you can actually design a spaceship shaped like a disc or a wheel, where the speed of the wheel and the disc will, according to Newton's first law, generate that inertia effect, because inertia is proportional to mass. And then v in this case would be the speed of the rotation, and r would be the radius of the turn, or in this case, the radius of a wheel and the radius of a disc spaceship. So now, also important, especially if we want to launch something in orbit of the Earth, is the escape velocity, which is the speed that an object needs to be launched up to enter Earth's orbit and not fall back to the ground. Because when you launch something up, this object reaches the highest point and then it comes back down. So what would be the speed in which you launch it up and it never comes back again? So that means that all the kinetic energy that you have on the ground will cancel out with the potential energy that it has on the surface, on the ground. And you can actually solve this equation to find the escape speed, the escape velocity on a certain planet. As you can see, m is the mass of the planet and r is the radius of the planet. It comes down to this equation that total energy is kinetic plus potential. But when you reach the highest point, you actually stop, right? You don't go up or you don't go down, meaning all the kinetic energy is used on its way up and it becomes zero velocity at the very top. But then it is in such a way that it cancels out with the potential energy and you're left with nothing. And then you ended up entering an orbit around the Earth and you never come back again. So which means the potential energy now doesn't become kinetic. In reality, orbits are not that stable and so forth. But assuming you want to launch something and not have that something come back down, that something will reach a certain height that is so high above the Earth's surface, and that by following the curvature of the Earth, it cannot reach the Earth ever again, and it goes in an orbit around the Earth. So this is what we call the escape velocity. So lots of things we can do in space and lots of equations, and this is just a scratching the surface of the knowledge of gravitation. So this was the second video on gravitation. See you next time. Everyone, today we're going to talk about electric forces and fields. So first thing to know is that electric force and fields arises from charges, right? So for example, an object can become charged when it acquires an excess of positive holes or electrons with a negative charge. Positive holes exist in the electron shells in atoms with missing electrons. So if you have an atom, you have the nucleus and you have the electrons. If there's a shell, if there's an orbit around the atom with a missing electron, that orbit has a positive charge, and we call these positive holes. When an atom loses an electron, it gains a vacant spot called a hole, which is positive. So if there's a vacant spot, it's a positive hole. If the spot is filled or it becomes neutral. Now, if there is a negative charge, if there's an extra electron in an atom, then the atom is no longer neutral, but it has a negative charge. If an atom has more electrons than protons, it has a negative charge. If the number of electrons equals to the number of protons, the atom is neutral. If there are less electrons than protons, the atom has positive holes and it has a positive charge. And this gives rise to the ions, the cations, and the anions and stuff like that. There are three ways for materials to gain charge. There is charging by friction, which is rubbing your hair with the styrofoam and seeing the static force between your hair and the styrofoam. So here we have a picture demonstrating a hair and a styrofoam. Whenever you rub your hair with the styrofoam, charges move from one object to the other, leading to the two objects becoming charged. During the rubbing process, the styrofoam loses electrons while your hair gains electrons. The result is that since unlike charges attract, your hair is now attracted by the styrofoam. Just like energy cannot be created or destroyed, only transformed, the number of charges is held constant. At first, the hair and styrofoam are both neutral. After the rubbing process, the styrofoam gains positive holes, which means electrons left the styrofoam and went into the hair. Notice that the net charge is still 0. Plus 3 minus 3 still gives you 0. Of course, when you rub your hair with styrofoam, not just 3 electrons will be transferred to your hair, but many more. This is just for illustrative purposes, of course. So the net charge is still 0 because that's the amount of charge that we begin with. Because everything in physics and in the natural world is conserved. Energy cannot be created nor destroyed, only transformed. There's conservation of mass. There's conservation of charge. There's conservation everywhere. Now, charging by conduction, that's another way of charging. When you bring a charged rod that touches another rod, charges flow and spread on both. So initially we have 4 electrons in the first rod. When they touch each other, the electrons spread out because the electrons repel each other. And because the electrons repel each other, they tend to move away from each other. So they tend to spread out whichever space there is. If the material is a good conductor of electricity, meaning it's a metal in which charges are free to flow, then it spreads out evenly. The net charge is still kept negative 4e, obeying the conservation law. The third way of charging is through induction. When you bring a charged rod near another rod without touching, so let's say we got a negatively charged rod brought near another rod, because the negatively charged rod has a negative charge, the positive holes will be attracted towards that, and the electrons will be repelled by the negatively charged rod. Now, what you can do is you can connect this bottom rod with a wire that is grounded. Yes, the ground conducts electricity. So you ground the rod and the electrons can escape because the electrons will still be repelled by the electrons in the rod. And that means that the electrons will escape to the ground, and afterwards you're going to have a negatively charged rod and a positively charged rod, and that's one way that's another way in which objects can be charged, which is through induction. Now, the strength of an electric field coming from a charge. If a charge has positive charge, then the electric field lines point away from it. If the charge has negatively charged, the electric field lines point towards it. That doesn't mean that there are actually arrows in nature. That is just for convenience. So one thing to point out, and that's something that was discovered by Isaac Newton, is that if you have a point source of gravity, or if you have a point source of sound, or if you have a point source of a field, if you draw a circle around that point source, the further you are from that point source, the bigger is the surface area of the sphere surrounding that point source. And because the area of a sphere is 4 pi r squared, 4 pi the solid angle, then the further away you are, the intensity of that field or force drops proportional to r squared. And this is where we get this equation, that the force between two charged objects is equal to K, which is the Coulomb's constant, 9 times 10 to the 9 newtons meter square over Coulomb square, being Coulomb's the unit for charge. The two Q's represent the two charges in question, the two charges that are experiencing a force due to each other, and the r square is at the bottom. The r square at the bottom comes from this r square over here. And of course, the 4 pi is incorporated into the constant because this is a constant of proportionality. So constants of proportionality, they are in the equation because when we place them in the equation, we can have we get the answers that we want. So this is what constants of proportionality are for. So K is a constant of proportionality, just like G is a constant for proportionality in GMM over R squared. Electric force and field lines, as you can see, the field lines point away from the positive charge and towards the negative charge. The field lines converge on each other, meaning they curl, creating a dipole when the two charges are oppositely charged. When the two charges are equally charged, meaning two positive or two negative, the field lines avoid each other. But even when the field lines avoid each other, you still have the field lines pointing away from the positive and towards the negative. So this was the first video with an introduction to electric forces. Hello everyone, this is part 2 video of the electric forces. Here we got, in this image, a negatively charged particle next to a positively charged particle, and there are arrows and lines between them representing the electric field between these two particles, which is causing their attraction. As you can see, electric field lines are only a description, a mathematical description about the geometry surrounding these particles, the field lines, the fields are generated by photons that are emanated from these particles, generating the geometry, which in this particular case causes the particles to attract one another because one is negative, the other one is positive. Electric force equations, F equals KQQ over R squared, with K being the Coulomb's constant, 9 times 10 to the 9 newtons meter square over C squared. Coulomb's constant is C, which is the Coulomb's not constant. Coulomb's unit is C, which is the unit for charge. Force can be attractive, such as a negative and a positive. Force can be repulsive when there's two positive and two negatives. Notice that the electric field lines, the vectors, point away from the positive and towards the negative. Notice that even when the force is repulsive, when you have two positive and two negative, the forces still point away from the positive and towards the negative. The field lines avoid each other, which causes a repulsion between the two, and the field lines converge on each other, curl on each other, forming this dipole where the particles are being attracted by the electric force. Here we got our gnome Zervina, and that's what he has to say. Electric field lines point away from positive charges and towards negative charges, regardless if it's two negative, two positive, one negative. Field arrows don't exist, but were created by humans for convenience, facilitating calculations. What does that mean? It means that in order for us to have a more mathematical and geometrical description of reality, of the nature of forces, it's important for us to have arrows for fields, arrows for forces, arrows for dipole moments, arrows for the magnetic field, and so forth. So we created those arrows so that we can make predictions, so we can better describe natural phenomena, in this case electric forces and fields. So if we look at the particles through a microscope, we're not going to see arrows there. We're not even going to see the field lines, but we created these structures to facilitate our understanding and our description, because we can only make measurements
if we have arrows, or if we have lines, if we have numerical, like for example in an atom, energy levels, we humans tend to make things numerically using equations and apply them to explain theories, and use laws and constants to in theories with equations, so that we can predict, because we can only predict numerically. We cannot say, oh, it's about 10 newtons, or no, we cannot say it's a strong force. It's better if you say 10 newtons, or you can say it's a weak force. No, how weak is that, or how small, how big? It's always convenient to give numbers, so that's why we have lines and arrows. Now, fields come from a source. So if you think of a source of a field, of a gravitational force, and so forth, we imagine a sphere surrounding that point source, and that sphere has surface area 4 pi r squared. And the further away we get from that point source, the bigger is the surface area in space surrounding that source, which means the field weakens proportional to the inverse square of its distance. And when we think of point source, if we imagine a shell carrying charges on its surface, the point from where the field is actually originating is in the center of the shell. And then as you move away from the shell, you're not measuring the distance between you and the surface of the shell, but between you and the center of the shell. And if there's a positive charge at the location where you are, it will experience a force. Electric force is measured in newtons, big N. Electric field is newtons per coulomb. Newtons per coulomb, we use C for coulomb, which is the unit for charge. Electric fields generate a force between two or more particles. So if you have an electric field alone, such as in this case, no force. But if you have an electric field and a particle, then there's a force. There's no electric force in the presence of a single particle. Here we got a particle saying, I experience no force by myself, because you will only experience a force if there's something besides yourself, if there's something besides one particle, which causes the attraction or repulsion of them. If you get the electric field and multiply times the charge, you get the electric force. Because electric field is newtons per coulomb, so if you multiply newtons per coulomb times coulomb, you get newtons, which is the force. Now let's imagine we got a sheet with charges, positive charges in this case, so we know the electric field lines point away from that positive charge. And of course, there's not only 4 charges or 4 positive holes in that sheet, but there's several. This is just for illustrative purposes that we have 4 particles, or actually 4 holes in there. Electric field lines pointing away from the positively charged plate. Now, when we place a positive particle on next to the plate, the electric field then becomes force from this equation right here. Electric field times charge equals electric force. But then because the particle also has a positive charge, the force will be repulsive and the particle will want to move to the right. Now, if we place a negatively charged particle next to the plate, the force will be attractive, because opposite charges attract, like charges repel, as we said earlier. And when explaining about this equation, F equals KQQ of R squared, one thing to point out is the mathematics of proportionality. You know, humans give meaning to things. Like I was saying earlier, arrows don't exist in the natural world. We put arrows there, right? Electric field lines also do not exist. We added the lines so we can have a numerical and a geometrical description of reality of that natural phenomenon. But we also use proportionality to describe things without knowing the actual numbers. For example, we know the equation is FKQQ over R squared. Now, if we, for example, we double the charge in one of the particles, so that means we're going to have twice as much force between the particles. And we know that just from proportionality. We don't know what the charges are. We don't know what their distances are. But if we double one of the charges, we double the force. Now, if we double both charges, now the force increases 4 times. So this is the mathematics of proportionality. You're talking about ratios and proportions. And a lot of things, actually everything in the natural world are ratios and proportions, right? There's the proportions for building a house. There's the proportions for writing a book. There's the proportions for medical surgery and so forth. Now, if we double one charge and we half the other, 2 times a half gives you 1, so there's no change in the force, and the force remains the same. Now, if we half the distance, it's going to be 1/2 squared, and the 4 goes to the top, and now you have 4 times the force. So if you decrease the distance between the two particles to half of its original distance, you're actually going to increase the force 4 times, because the force diminishes with the inverse square of the distance. If you half the distance, you increase it 4 times. Now, if you double the distance, you decrease the force to a fourth of what it was initially, because of the inverse square law. Now, another interesting thing, if you triple the distance and you have one charge, since we're talking about proportionality, let me add a capital C here. So then you're going to have 1/2/9, which is 1/18 of a force. So you can change multiple variables and equations at the same time, and you're able to get the proportionality. So as you can see, is science invented or is science discovered? Are these arrows in the actual natural world? Does electric fields have arrows? What are electric field lines? What is electric fields in the first place? Because we know it's a field of photons. We know it's energy coming from the particles. But how is this energy coming out of the particle? Or is the particle losing energy because it has a charge? But it doesn't lose energy that way. So there's many things that we just don't know. And humans, scientists, they use reason and they try to create everything that they believe and that they study. So a lot of things that we do, most of it was invented to see if we can actually make discoveries. And we end up making discoveries and have a better understanding of reality. Thanks for watching.